Hello, this is Amanda Matson again. I am making a video on hypothesis testing when you have more than one variable. Specifically, when you have a categorical variable and then one that's a numerical variable. And so I'm really looking at one variable across multiple categories. I have, since it's a hypothesis test, I'm always starting with my hypotheses. And so my null hypothesis is that the spread of temperatures in Iowa behaves the same every month. And my alternative is that the spread of temperatures in Iowa behaves differently for at least 1 month. So, like maybe January is off. I don't know, but at least one of them is off. And so, my month, this is my category, and then this is my number. And so, I've got 12 months, so however many categories, and then a bunch of numbers that are spread out by category. Okay, like I've done before, whatever test I run, I'm going to save it into results so that I can mess with it later. This is my Iowa soil data. So same data I've been poking at for a little bit now. And I'm pushing it into this linear model. All right, remember L stands for linear. So it's not a 1, it's an L, where my spread of temperatures is a function of the category they're in, so the month. And so remember that this is the number value is a function of the category. So like that's the way you split it up. Lost my period. This little dot here means that my spread and my month come from Iowa soil. And then this parenthesis ends my linear model, and I'm pushing it into this Anova command, which is analysis of variance. There we go. So that's what Anova stands for. Okay. Delete that and run. I have results. So I have my Iowa soil, got my results. When you start typing results and put the $sign in, you'll see this one down here. It's your probability number. And I run that, and that's my p-value. Cancel. My p-value is 5.4 times 10 to the negative 33. And if I put that into my negative log base 2, then that tells me how many coins that's the equivalent of. And so I get 107 coins. And so the odds of the null hypothesis being right are the same as flipping 107 coins and getting all heads. To which we say, no. No. So if my null hypothesis is definitely not right, then I go to the alternative. So null hypothesis. This is rejected. Come back up here. And so I can copy this sentence. Bring it down here. Hashtag space. Therefore, the spread of temperatures in Iowa behaves differently for at least 1 month. And so that's what is going on for that. And this is in a notebook because I'm seeing like that behavior. If I'm looking at something different, my other data set is about air quality. The average, the air quality, AQI, air quality index, is the same in each state. And the alternative is that the air quality index behaves differently in at least one state. And so I've got my null, and then my alternative is that something misbehaves. Results, instead of Iowa soil, it's my daily AQI by county. And this time it's my AQI by state. State name. And run. And then this time my p-value, oh, it's thinking. My p-value says 0, which means it's tiny. And my number of coins is infinitely many. Is flipping a very large number. Coins and getting all heads. And so I'm still rejecting the null hypothesis. And so then I can say my error quality index behaves differently in at least one state. So that one goes there. Okay. So this is that analysis of variance. I was running like 50 states, I wouldn't think that they would behave the same. So maybe if I had different data, I'd get different results. Or maybe if I looked only at winter months, then I'd get a similar spread. So those are things that you could do. But you make sure that you're describing what's going on. You've got a column that's got your categories, column that's got your number. This is actually a quantitative variable if you want the fancy word. That's across multiple categories. And then this is your number again, and then this is your category. And then you're running an Anova test. And that's it.